Good afternoon and welcome to today's class. So we are going to continue from where we stopped. We were looking at structure and bonding, and today I want us to focus on physical properties of molecular structures. So we saw that for covalent bonding, so we have said that for covalent bonding, there are two structures that arises, and one is molecular structures, which I remember saying is common in molecules. Such as CO2, oxygen, nitrogen, hydrogen, chlorine, etc. Then the second one is covalent giant covalent structures. So this one is seen in diamond structure, graphite, and silicon 4 oxide. Silicon 4 oxide. So when you look at these two categories, when covalent bond takes place, you can end up with molecular structures, and this is majorly common in molecules, which we have also drawn some of their structures. Then we have got giant covalent structures, which are seen in diamond, graphite, and silicon 4 oxide. This giant covalent is also called giant atomic structures. So some books will talk about giant atomic structures, which is the same as giant covalent structures. So I want us to look at the physical properties of molecular structures. So physical properties include things like solubility, melting and boiling points, electrical conductivity are the physical properties we are going to look at. So let's start with electrical conductivity. It is important to note that molecular structures does not conduct electricity. So they do not conduct both heat and electricity. So why do you think they don't conduct heat and electricity? We have seen earlier that for any substance to conduct electricity, there are two parameters. One is that there must be some delocalized electrons. Two, there must be mobile ions. Mobile ions. So if they do not conduct, it means this substance they do not have. So this because they do not have mobile ions or delocalized. Electrons in their structures. So it means that they neither have mobile ions nor delocalized electrons in their structures. So that is the main reason why they do not conduct electricity. The second physical property that you want to look at is melting We have seen earlier that melting and boiling point is associated with bond breakage. So we must know that what type of bonds are being broken when these substances undergo melting process. So we know that these substances, their atoms are bonded covalently. That is to say, the atoms in the molecule are covalently bonded. But this is very important to note that although the atoms are covalently bonded, the molecules are held together by intermolecular forces, e.g. weak van der Waals and also hydrogen bonds, which is common in water. So, these intermolecular forces, like the weak van der Waals, they are very weak to a point that they require little energy. You just need to apply a small energy to overcome them. So, therefore, they have low melting and boiling points. Because the weak van der Waals, because the intermolecular forces, which I've said are two, most of them have the weak van der Waals, but there's also some molecules that have hydrogen bonding, especially water molecule and also ethanol. They have some hydrogen bonding. So most of them have the intermolecular forces which are weak, because the intermolecular forces are weak and therefore little energy is required so to break those intermolecular forces, you need to apply very small energy, and therefore they will have very low melting and boiling points. So it is also important to note that melting involves breaking the intermolecular forces, not the covalent bonds in the molecules. So melting and boiling For example, if you have got a molecule of chlorine there, another molecule of chlorine there, these molecules, the two chlorine atoms are bonded covalently, but the forces holding the molecules together these are what we call the intermolecular forces, the intermolecular these are what we call the intermolecular forces. And in case of a chlorine atom, it is the weak van der Waals, the weak van der Waals forces. So when you want to melt it, you don't break the covalent bond here, but you just break the intermolecular forces. That's why they will have low melting and boiling point. So the next one that I also want us to look at is what we call solubility. So it is important to know that most of molecular are insoluble in water. Why? Because they do not have polar ends. So which means they do not have the charged ends like ionic compounds, which have charges that can be hydrolyzed, that can dissolve in water. But there are some, such as sugar. We also have ethanol, can dissolve in water, so dissolves in water to form a solution. So they can dissolve in water to form a solution. So generally, most of them are insoluble in water. And these ones, which can dissolve in water, is due to the presence of hydrogen bond. Due to the presence of hydrogen bonding in them. Hydrogen in them. So this one has some hydrogen bond that allow them to interact with the polar water molecules. and therefore they dissolve to form a solution. So the relationship between the strength of the intermolecular forces can also dictate some of the properties of these molecular structures. For example, so you want to examine the strength of intermolecular forces. So you can be asked to explain why water molecular mass is 18 is a liquid at room temperature. While hydrogen sulfide gas molecular mass 34 is a gas at room temperature. This is a common question in KCSE that exhibit those kind of bonds and why they have high melting and boiling point. So I want to give you one before we look at the giant covalent structures, and you are going to explain to me why it is possible to have those kind of scenarios. So just a small, I can call it assignment that briefly explain why carbon 4 oxide now you know the CO2 is a gas while water is a liquid at room temperature. What is a liquid? So water is H2O. Let me write the formula. The liquid yet the carbon dioxide has higher, yet has higher relative molecular mass than water. So try to relate based on the strength of the intermolecular forces that we have seen how you can answer that question. Moving forward, I want us to look at giant the second type of structures that arise due to covalent bonding, which is giant covalent stroke atomic structures. This kind of structure is formed when atoms bond indefinitely. Structures formed when atoms bonds indefinitely through covalent bonds. So when you have the whole structure, there is nothing like intermolecular forces. All the atoms are bonded covalently. You end up with what we call giant covalent or giant atomic structures. This one is seen in substances such as diamond. I've said this earlier as part of the introduction. Diamond, graphite, silicon, 4-oxide. We have the graphene, etc. Some of the common giant covalent structures. So in all these structures, the atoms forming the structures are all covalently bonded. There is no intermolecular force of attraction in all those structures. So when, for example, we take like diamond, and one thing about diamond, that it is an allotrope of carbon. Diamond is an allotrope of carbon. In other words, carbon has various ways in which it exists in the physical state. So one way you can find carbon existing is through diamond. So there's also some other allotropes or some other physical states in which you can find carbon element existing. So in diamond, each carbon is covalently bonded to 4 other carbon atoms. So each carbon, because carbon can form 4 different bonds. So each carbon atom is covalently bonded to 4 other carbon atoms, forming an octahedral structure. So in graphite, in diamond, all the valence electrons are used in bonding. All of them are used in bonding. And that's why we are saying each carbon atom will be bonded to 4 other carbon atoms covalently, forming an octahedral structure, which is now the giant covalent structure. Good. Now, if you want to sketch the structure of graphite, you can have this. So that's the carbon bonded to 4 other carbons. So each carbon is bonded to 4 other carbon atoms. So this is repeated. This is repeated So for example, if we take this carbon, you'll find it is bonded to 1, 2, 3, then 4. So that is how the bonding takes place. When you take, for example, this carbon, it is bonded to 1, 2, then 3, and 4. So all of them, that is now the example of how the octahedral structure will be formed. Next, it is also important to know that diamond is the hardest known substance. So it is the hardest known substance, and this diamond can be used to make drillers that can make holes in metals, in metallic surfaces. It has a very high melting of 3,700 degrees Celsius. That's a very high melting point of 3,700 degrees Celsius. And all this is attributed, these features of diamond are attributed by the strong covalent bonds of the carbon atoms, So that strong covalent bond is why you will find that diamond will have the high melting point of that, and also it is one of the hardest known substance. Let us look at graphite. This was another allotrope of carbon. We want to look at how is graphite structure different from diamond structure. So it is also important to know that in graphite, each carbon atom is bonded to 3 other carbon atoms. Each carbon atom are bonded to 3 other carbon atoms. And when that structure repeats itself, we'll end up with an forming an hexagonal structure, So remember, carbon has 4 electrons in the outermost energy level. And therefore, when you just use 3 for bonding, then there is always 1 electron which is remaining unbonded. And this electron will be delocalized within the structure of graphite. This explains why graphite is a good conductor of heat and electricity. Because there is 1 electron which is delocalized, and that is what conducts electricity. So, only 3 electrons are used, only 3 valence are used for bonding. And therefore, the 4th electron is delocalized. And therefore, the 4th electron delocalized in the structure. So, this 4th electron is what now conducts. So, this makes graphite a good conductor of heat and electricity. Of heat and electricity, because of the presence of the localized electron. So, if you want to draw the structure of graphite, the hexagonal structure, so that's 1 layer. So that's 1 layer, so you can have this. So you can have more of this, and you have got other layers here. You can have this kind of another layer there. Like that. So this one is the hexagonal layer of graphite, hexagonal structure of graphite. Each carbon atom is bonded to 3 other carbon. For example, this one is bonded to this one carbon, this another, and then the other one. This one is bonded to 3, this one, and this one. So all of them will behave like that. Then lastly, just in conclusion, it is also important to know that due to its electrical conductivity, graphite is used in electrolysis as an electrode. This is very important. Most of the electrolysis processes, they use graphite as an electrode, the cathode and the anode, because of its electrical conductivity. Then lastly, silicon 4 oxide the SO2. So in that structure, the silicon, the SiO2, the silicon atom, each silicon atom, each silicon is covalently bonded to 4 oxygen atoms, to 4 oxygen atoms, forming a giant covalent structure, forming a giant covalent structure. So that brings the end to our today's class, and I just want to encourage you to also look at some of the key points that I've insisted on, because those are where the marks are. So thank you very much, and looking forward to the next topic that you are going to start, which is now metallic bond. So our next class, we shall start metallic bond. So it is important also to read ahead of me and also prepare for that class. Thank you very much.